distribution function, and it means that the polarization density becomes of second and higher orders in a self-consistent turbulent field phi. In this talk, I'd like to address other sort of nonlinearities in the polarization density, which appear if one includes high-order corrections in the gyrokinetic derivation. I dub these corrections mesoscale nonlinearities because they should be not that important if you are in the coplasma. This is the status of the art in the area. The approach to the mesoscale sort of gyrokinetics has been initiated by Alain Brizard with his work where he considered the gyrokinetics in the frame rotating with the fluid velocity with u0. This is a resulting Poincare-Cartan form, the Hamiltonian function, and the generalized vector potential with u0 being in Alain's work fluid velocity. Taxon has used this approach to address the pedestal, the gyrokinetic and pedestal regimes. In his approach, u0 was an E cross B velocity with E being an electric field associated with a pedestal electric field. There were various improvements in this area. A couple of examples. There was a paper of Miyato and Scott where they considered u0, which is essentially harms u0, to be time dependent, and then they shifted all the time dependent quantities out of the symplectic structure into the Hamiltonian in order to get rid of time derivatives in the equations of motion, which would be somewhat cumbersome from the numerical point of view. There was also a paper by Kawamura and others where they suggested more correct expression for the frame velocity rotation for u0. In the Hahn-Brizard approaches, there was a requirement u0 should be a slow function comparing with the gyro radius, slow dependency on the spatial coordinate. And one may ask the question, how could one address this sort of gyrokinetic theory in the case if u0, which means phi large, the potential associated with this E cross B, if this phi large changes on smaller scales, which can be even comparable to the gyro radius. So this is the subject of this talk. Again, some illustration for what I just have said. We have usual microscale gyro radius, usual macroscale system size, and a continuum, a bunch of scales in between, which are mesoscales. And in coplasma, there is nothing special happens in this region, but in the H plasma or various boundary layers, this is the area where something can happen. And this is the area where we set our mesoscale potential phi. So you can see that Hahn-Brizard, Miyato, Scott addressed more or less this part of the spectrum of scales, and we try to address this part of the scale spectrum. So this is some ordering. We split the potential into the mesoscale component phi large and microscale component phi small. A standard gyrokinetic ordering is assumed for the microturbulence component, which means that for example, means that the associated E cross B rotation is of order epsilon comparing to the thermal velocity, so drift ordering. And for mesoscale field, we assume that rotation is stronger, but still subsonic. We order it formally as square root of epsilon comparing to the thermal velocity. The length of the microturbulence can, as usually, go down to the gyro radius, and the mesoscale length is of course larger, but must not be much larger than the gyro radius. Can be comparable to it. So for the subsonic velocity, we start with a traditional, usual Poincare-Cartan form, like that, with normal generalized vector potential. We do it in lab frame, so we do not include u0 in a star. This is a Hamiltonian function which we like to transform. It has two components, microturbulence, mesoscale components. If you like to derive the polarization density within variational principle, polarization density which corresponds to the microturbulence, we must go as usually to epsilon square in our derivation, which means.
Sorry, in this Hamiltonian, square root of epsilon on the macro scale phi.
Mesoscale, yeah.
Oh, that's a mesoscale phi?
Right.
The macro scale phi would be of order unity.
Yes, I do not include it. So I do not have macro scale file. I have two components, mesoscale and microscale. So I have microturbulence. This is like normal gyrokinetic theory, which you have in coplasma, plus this component. If you would like to include macro scale file, then perhaps you should do it in V as Alan Brizao, Taixuhama or others did it, which means that you modify generalized vector potential with U0. So you go in the frame which is associated with the E cross B velocity of this macro scale file, and then the ordering applies, and I think you can do the same here. But this I have not done. I mean, it should be technically not a huge complication, but I did not have not done it.
Actually, for a macro scale phi of order 1, as long as it's on wavelength, you don't need the U. It's only if it flows order 1. So the theory is the same even for macro scale.
Micro scale or macro? You mean system size or gyrokinetic?
Even system size phi, as long as the velocity is small.
So that's what I'm confused by.
Yeah.
Is, if the macro scale phi is small.
Yep.
I'm sorry. If the macro scale velocity is small, so the macro scale velocity is order epsilon v thermal. E phi over t is order unity, so there is no square root of epsilon.
Let's talk about mesoscale phi. Yeah, okay. How do you get square root of epsilon as this equation?
He's not known macro.
How did I get it? So the thing is like that. This is how I order the equals B velocity associated with what I dub mesoscale phi. It is ordered as square root of epsilon times thermal velocity. So this is of order square root of epsilon. Means rotation is strong, but still subsonic. If I allow phi to have scales down to gyro radius, then exactly this ordering appears for the mesoscale electrostatic potential which enters the Hamiltonian function. This is how I did it.
The way I like to think about it is that you introduce this new scale which is comparable to the square root of the gyro radius times the macroscopic scale, so that when you take the ratio of that mesoscale over the macroscopic scale, you get a square root of epsilon.
So anyway, this was initial motivation, but perhaps there are also other applications for the results. I don't know. So anyway, this is a Hamiltonian. So the physics is here. And now we start our transforming. We must go to the fourth order in square root of epsilon in order to be of second order in epsilon, which will give us the polarization density within variational principle, polarization density associated with psi small. So, as usually, Hamiltonian is split. Well, you can see how it is split, and we expand the particle Hamiltonian, in powers of epsilon, just more or less the same. And this is a reduced Hamiltonian, which is also expanded in powers of square root of epsilon. Yeah, this is what I said about the ordering. So now we remove gyro dependencies from the Hamiltonian.
On a scale down to relative, you need somewhat larger.
Somewhat larger, but can be comparable. So,
Which somewhat larger or comparable?
Somewhat larger, which means comparable. Somewhat larger up to comparable, up to so that at some point you don't have a difference between phi large and phi small, and then what we derive here becomes just nonlinear correction to the polarization density with respect to single potential phi. But this was initial motivation. We have considered it like mesoscale component, microturbulence component. But this is perhaps a bit, not just that. So starting from mesoscale and down to microturbulence, which is strong, so that you get phi squared contributions into the polarization density. So we apply Little-Sum technique, and this is a Hamiltonian Little-Sum technique, which is sufficient here because the symplectic structure is not going to be changed in the course of the transformation. This is a usual Litton's form expressions, which you can find in various review papers, and these are few orders of perturbation theory of expansion, which can relatively easily be derived. But what happens at next orders, at higher orders, the number of terms sort of explodes, because you have to expand each exponential here and further, and you have to expand this Hamiltonian function. You have just 3 pieces now, but if you have more pieces, it becomes really ugly and cumbersome. The good thing about this little sum is that it is nicely.
Sorry, one more question. How are you ordering the magnetic field variations scale? I guess, is that macroscopic, so it's
Yes,
epsilon
yes.
squared or something?
Yes. It's a usual magnetic field which we do not have electromagnetic perturbation, electromagnetic component in the
I mean the
microturbulence or mesoscale field so far, but one can include it, of course.
Yeah, I'm asking that question sort of in connection with comment with I guess the Ivan's talk, and you know, I had a page on the same issue. Magnetic field variation terms come in, but you're not treating the guiding center to high orders.
No, that's not. That's not happens. That's not happens here. No. That's not happens. It's like Lego. You can put various things together, but this is just one of stones, perhaps. Maybe.
You've got mesoscale equals B flows, is that right?
Yep.
And then these are fast equals B flows, they're fast and diamagnetic.
Yep.
What creates these?
Okay. So it's fast but subsonic, and perhaps some transport barrier, some pedestal sort of thing, something like that.
The flows in the pedestal, though, are in fact diamagnetic in size, right? So they're smaller than this.
Well, this can be, in fact, anything which has sufficient field strength, which is stronger than the usual drift ordering, and still has scales comparable to the gyro scale. So I was thinking about some coherent structures on plasma edge, or perhaps turbulence, which is stronger on the edge. And if you consider turbulence, edge turbulence, which is stronger than the core one, then maybe you don't need anymore to make a distinction between phi small and phi large. Then you have just phi large, and you go to higher orders. I mean, or just phi small, and you go to higher orders. But the initial motivation was to do it within, yes, a sort of mesoscale argumentation. And I was thinking that pedestal flows are stronger than diamagnetic, actually.
Pedestal flows are comparable with the diamagnetic.
I mean, you know better, I don't doubt it, but this was my idea of the thing. Yeah, so this is technical thing what happens at next orders, and the good thing about Litton's form is that it can be nicely formalized, so that in principle one can use computer algebra for that. I did it as a sort of, well, it helped me a little bit, but one can extend it. So I use this simple script to produce higher orders, and well, I don't know, shall I? It's simple. The main message here that it doesn't cost me efforts to write something like that.
How do you know it's right if you've done it on the computer?
Pardon me? What do you ask?
You know it's right if you've done it on the computer.
How do I know that the finite result is right? This is your question, right?
That the algebra is right.
That the algebra is right. Okay, this is a good question. How do you know that your particular algebra is right and you did not have much risk, too much risk the day
didn't
before?
do it on the computer. That's why I
What?
asked. Because I did it with pen and paper.
Yes, but
That's
how
I
do you
asked
how
Alex to check it.
how do you know that? Yeah, how do you know that there is nothing wrong in your calculation? I mean, there is always some possibilities to make an error.
I'm just asking. Look,
Yeah, of course.
I'm not doubting that it's
I
right.
can be-
I'm
I
just
can-
saying when I do algebra on the computer, I can't. Maybe it's just my particular psychological problem. I can't trust what.
Of course,
So
of course.
there are a couple of things you can do. One is you can try to do the same thing with a completely independent symbolic
That's right.
algebra program,
Of course.
and then you can try to do the calculations a few different ways with the same program.
Yeah.
Uh-huh.
It's usual thing. You check your analytic computation. I suppose too with some tests. So it's absolutely the same.
How many orders are you going to have to work through?
I'm going to have just 4 orders. Actually, just 3 orders are sufficient. But this thing gives me possibility to go to arbitrary orders. Of course, not everything. I mean, it's not that I magically obtain a result out of the computer, but some pieces of the computation can be nicely formalized, and this is what you can do with things like Lie transform because of
If
nature.
somebody can have a computer to code up the resulting equations as well,
Yeah, it would be great. Yeah.
we can put the whole thing
Yeah.
on an industrial basis. These codes, Mathematica and Maple contain code generators. They'll write portion for you.
Alan,
Felix,
didn't
you
we
don't
have to
have
work
worship
through
them.
fourth
How many
order
orders do you want?
thesis?
I'm outdated, man.
I thought you had to go that high.
I went to third order and guiding center, but fourth order was not necessary.
Not even a constraint for fourth order.
No.
Okay.
So, yes, another question back on the ordering. Sorry, go back. So we had doubts about whether flows larger than diamagnetic are important. The other question is with the disordering. That was the velocity ordering, rotation, the square root of. So that actually says that the gradients of those potentials are stronger than the profile scales.
Yep.
So that's sort of a again a different from any of the other orderings that I've seen.
Yeah, for example, if you have this root jumping situation in stellarators, I think this is what happens there. You have strong gradient in phi in electric field because of different roots
But
here,
not in P.
but not in P because diffusion is, neoclassical diffusion, stellarator neoclassical diffusion is strong in this area, I think, and then it flattens. It makes things associated with P much larger scales, much smaller variation that phi does. So this was sort of, but I must admit that just to be frank, absolutely frank, there are things which sometimes you have physical problem, and then you look for solution of this problem. So problem looks for solution. Here the situation initially was a bit different. We would like to play with different orders and things like that, so we had a solution. And this is situation solution looks for problem, It's an inverse kind of, I must admit that this is really the situation like that. So we had this expansion at some point with Alan and just how to do it. Yeah, so computer algebra helps, and this is example. I could just with one simple call produce 6 order of perturbation theory Hamiltonian function in terms of Lie transforms. This is what comes out directly, and I would need a bit, well, I would say some time to do it analytically, and I might make some mistakes because it's cumbersome, tedious, and ugly and uninteresting.
It understands about non-commuting operators when it does the experiment.
Yeah. I know the issue. So I need to take that into the account. I know the issue. Yeah. So back to the Lie transform. These are the, well, in the Hamiltonian Lie transform, what you have to do formally, you have to solve the equations for the generating functions. These are the equations up to the fourth order, written in terms of the Lie derivatives. These are the Lie derivatives, defined in terms of the generating function and Lie operators. These are the Lie operators of different orders. And this equation must be solved order by order. So this, if we jar average area of those equations, we get Hamiltonian of the corresponding order, first, second, third, and so on. This is how these Hamiltonians look like in terms of the generating function and fields. So we need to solve equation for generating function to express Hamiltonians in terms of the fields and Poisson brackets. And here you can see already things which appear and which will give you polarization density, so for your polarization of procedure. So start with second order gyrokinetic Hamiltonian function. This is a first order equation for the first order generating function which you need, and as usually here this quite a complicated equation appears, and actually it must be solved using multiple scale approach. This thing is ordered. So this the fastest term appearing here is that one, and usually one solves for it and truncates the solution. I do also few higher orders of magnitude. Well, I go a bit further, but this will not be really necessary for the order I want to have in the polarization density. And then substituting the solution of S1 into the Hamiltonian function, we get the second order Hamiltonian equation. This is a polarization density part. This is a part which everybody also knows, but I think nobody uses. Almost nobody, in the codes at least. The equation for next order generating function, again, I use here the multiple scale expansion, and these orders are associated with scales appearing here. This is the largest, fastest scale associated with the gyro rotation. So S2, here this notation appear like by one knows those notation from other papers. And this is expression for the third order Hamiltonian function in terms of the potentials, phi large and phi small. If at some point you do not make any distinction between phi large and phi small, you just consider higher order correction to the usual Hamiltonian function, or you can guess what you get. Normal, you can guess what you get. You should perhaps zero this one. You should zero phi small, and this is the piece which would appear the higher order correction to the usual gyrokinetic Hamiltonian function.
Why do you say that first term is zero?
I'm saying that here I'm doing a mesoscale plus microscale situation. So I have phi large and phi small. But I could use exactly the same derivation to get higher order corrections to the gyrokinetic Hamiltonian function. Usually one truncates Hamiltonian function at the second order. And we had a discussion 2 days ago which suggested that the Hamiltonian function should be truncated at higher orders to satisfy momentum transfer condition and things like that. So in principle, this is a derivation for such corrections. But then you do not need to make a distinction between phi large and phi small. you can just throw away one of the pieces, which would be phi small in this case, because I go to higher orders in phi large, and this would be the correction then, which comes out of my calculations. Fourth order, I will not show, but I went to that. And so for an Hamiltonian function, we can apply the usual variational principle, which has been discussed 2 weeks ago at the beginning of third week, constructing the action in the extended phase space, and then one can apply variational derivatives to the action with respect to the field. I have here two fields. I have phi large and phi small. So far I make distinction between them. If I apply variation, I want to have a polarization equation with accuracy up to phi squared. If I apply variational derivatives with respect to phi large, then I need just h3. h3, 1 order of magnitude less, because of the variational derivative one has second order corrections to the polarization density. If I want to do this through phi small, I could do it making a variational derivative with phi small. I need to go to the fourth order in terms of square root of epsilon, because phi small is of second order in terms of square root of epsilon. This I have done too. It was a cumbersome calculation, but it was greatly simplified by the Leibniz rule, which you can use so far you apply. So far you use partial brackets, so you can simplify your calculations, your algebra, using certain basic rules and formulating everything on a basic level without going into much of details. Yeah, and I compared it, and the result was the same, using fourth order and using third order. So this was sort of benchmark I did. This is a quasi-neutrality equation without, well, how it appears out of the variational principle. You can recognize, well, usual piece, polarization density, and of course the density itself, and you can see this correction, which is of second order and which, well, appears in this derivation. This expression is nice and beautiful, but perhaps it is a good idea to make some limit, to compute some limit, just to have everything in a more simple form. So I do long wavelength approximation. This is what comes out of the long wavelength approximation. The usual polarization density, and this correction, which is of the next order in phi. And formally, if I apply this ordering with square root of epsilon, this thing in terms of phi is of the same order as this one.
You don't have to assume anything about the distribution function here, is that
No, here I haven't. At this point I haven't.
right?
No.
You do not need to, because it's
No.
not-
I expand to, well, second, fourth order in K perp, and then just do partial integration, and I don't need to assume something about Maxwellian and things like that.
So, I will be starting with that equation later. And then there's, I think everybody knows now, on the right-hand side, that is not the true NI, that's in physical space. It's a guidance and a contribution to NI, and then the polarization contribution to NI.
Yeah. I relate them to the higher orders, to the next order. So I want to simplify this equation even further and introduce this sort of velocity, which is almost equals v, not exactly, but almost. And then I can cast the polarization, but I can cast the quasi-neutrality equation in this form. Well, it looks simpler. There is, well, it's sort of no approximation. I mean, in this transition, almost no approximation. And this is a momentum. This is sort of energy flux. Not know if it helps, but looks simpler. And I can define, I'm not the first who does it, so I can define the polarization vector, and then I can write and normalize everything to the ion density, and then I can write the quasi-neutrality equation with high order corrections, especially well, in a very simple form, and this is a usual polarization test. So you see it has divergence, total divergence of something, and this is a usual gyrokinetic polarization vector, and this is a correction. So it was that large, it can be done, but sorry, that small, but perhaps it helps you for interpretation. Okay, so now we consider the gyrokinetic Vlasov equation, particle energy, and equations of the motion at some point. As usually, one can derive the Vlasov equation out of the variational principle through this Eulerian constant variations of Lambrisa. And well, this is a Hamiltonian which enters here. If you want to keep energy conservation things, perhaps we need to include also H3 if you solve the quasi-entropy equation with high order corrections, I assume. Well, I did here also some sort of wavelength approximation, and I'm not the first one who does it. This thing is, of course, mu E squared, the energy associated with this equals v sort of velocity. And so far we have Hamiltonian function. We can easily derive, just taking Poisson brackets, the equation.
Sorry, on the previous slide, so H3 was still linear in phi, in little phi.
Yep.
And then I guess the question I have is, does it conserve, and does the system conserve energy with respect to the small scale phi fluctuations?
Well, I assume so far. I mean, I have here.
Because I ask it because the normal, in the standard theory, you need quadratic order and in phi, phi, the normal H2 to have.
Yeah, you perhaps this. Yes, I understand what you say. This appears in the fourth order. If you go to the fourth order, you find out phi squared, and perhaps for that you must include it in the Hamiltonian function. I shall assume. Yes, you can do it. I don't have it on this transparency. Yeah. So coming to the equations of motion, I think this is also sort of thing other people. I mean, these terms appear, for example, in Kerry-Brizard review. We have drifts, our usual parallel motion, usual magnetic drift, usual E cross B drift. Here is curvature drift in this B star, and there is an additional piece which you can write in a long wavelength approximation like that. And this piece is related to nabla E squared, and this is sort of ponderomotive force, so you get some kind of ponderomotive drift motion at higher orders. And similar situation is with the parallel force, usual mirror force, usual parallel electric acceleration. And here is this ponderomotive acceleration. Well, ponderomotive drift is dependent on charge, and of course it's much stronger for ions. Okay, so I would say I can do summary. There might be some new regimes on plasma edge, and these regimes are addressed by many people. There will be few talks in this workshop. So a sort of mesoscale physics appears in these new regimes, and this mesoscale physics needs sort of mesoscale gyrokinetics. This is one example of such attempt. We have found in this talk nonlinear contribution, mesoscale contribution to the quasi-neutrality polarization density, to the quasi-neutrality condition. We have found, well, I have shown, you knew perhaps, ponderomotive contributions to the gyrokinetic particle energy and equations of the motion, and it was not initial motivation, but nevertheless, perhaps if you don't make difference between phi large and phi small, then this suggests a Lie transform approach to the derivation of higher order corrections to the quasi-neutrality condition, to the polarization density, which might be related to the discussion around moment of conservation issue and tokamak. Thank you.